Stars. What are stars? Well, we've talked about that. Some, they're to our eye, they're glowing dots of light. Are they all the same size? Are they small and close? Are they big and far away? Are they all the same distance? All these questions arise. As you know, we're going to talk about the range of stars, how stars start in this video. And I encourage you to go outside. You know, really, we got to get outside. And you can do a video, or excuse me, a search for starry night. So I did starry night images. We can go to images here, and we can see all kinds of pictures. Now, some of these pictures, of course, you would not see with your naked eye. Most of these pictures, you wouldn't see this many. You'd need to start with binoculars and move to telescopes, and then even move to cameras and extended exposure. But think about the dots. You know, what are these dots here? And you take a look at some of these pictures, and you can go to NASA and take a peek. What are these? What's out there? Milky Way just was a strip in the sky. What could it be? Okay, so we're going to talk about these. I encourage you again to take a look and just pause and notice that you could ask that question. You could wonder. And we started in this course of things wondering about things. So stars, a few things to know about stars to get us going. No stars appear green or purple. Why? They appear reddish or orange or red-orange, yellow, white, blue, but they don't appear green or purple. And if you recall Wien's law in that discussion about how things glow, then you'll see that when you're getting a lot of green, you're also getting a lot of the other colors. And the other colors combined give us, of course, white. And if you're getting purples, not just getting purples, you're also getting these colors, right? And so you're going to get a blue-white. And so it's that combination of frequencies that go into our eye, and that combination gives the experience of color. So that's interesting to notice. Now you might see stars on the horizon twinkling, especially, say, Sirius on the horizon. Boy, and you'll see it twinkling a rainbow of colors. Ever notice that? Why is that? And that has to do with the atmosphere, spreading out the different frequencies. They're all there, because you might see Sirius in the sky as white, but that's all the frequencies. And as they come through the atmosphere, they can separate. And you can see this just wonderful diamond-like quality of all these colors. So the idea, keep in mind galaxies, like in our last video, right? Galaxies, galaxies, galaxies. These are enormous, absolutely enormous. And within the galaxy, we have giant clouds, giant molecular clouds, giant clouds, cool clouds within a galaxy. And in those galactic clouds, many stars form. Stars, when they form, they're all gas, and they stay all gas. They are all gas. There's no liquid in a star like we see in planets. So don't think of this. Right? Don't think of that. There's no liquid, and there's no solid. There's no solid anywhere. There's no solid surface. There's no solid core. There's no iron core. It's gas all the way through. Right? It's gas all the way through. Well, so these dots of light, look at it, really think about it. Just remember, those are just gas balls. We're surrounded by hot gas balls in space. It's crazy. What's it take to become a star? Many people ask that. What does it take to become a star? Well, first you got to get on American Idol, and then, you know, practice, basically. That's the answer. Practice, practice, practice. All right. So that's it. Right? You need enough gas to have enough mass. I love this. We're going to use this. You need enough gas to have enough mass, to have enough gravity to pull very slowly together. Pull together. And it pulls so strongly that it keeps squeezing and it gets hot. So it pulls itself together strongly enough, it'll heat up, and that means that the gas inside of it, important, gas, all gas, the gas gets hot, and that means that the gas is going fast. Cool gas, the atoms are going slower. The atoms and combination of atoms called molecules are going slower. But as you get hotter, you get enough gravity, it keeps squeezing, containing that gas. Hot gas can't get out, it's all packed in there, squeezing in. And what happens then is that the protons, which do not like each other, remember, electrically, protons push each other apart. And as they get closer, they really don't like it. It's like, get away, remember? But if you get it close enough together, instead of the electric force, there's still a strong electric force, they're still pushing apart, but there's another force, it's called the strong force, or the strong nuclear force. But there is another force that holds the centers of all of our atoms that make everything up, right? The gas, the air I breathe, everything. Those atoms are held together in the center by this strong force. And what happens, the strong force is actually very weak, but when you get it close enough together, you've heard this before, they fall together in a sense, where this strong force takes over and they fall together. And as they fall together, they snap together, they lose energy, and that energy is given off in the form of light. Light is not energy, energy is not light. So it doesn't give off energy, it gives off light, which has energy. Gamma light, remember that? The highest frequency of light, highest energy of light. So this makes stars shine. That's it. That's what makes stars shine. Okay, that's what powers every star. We'll come back to that. Nuclear fusion. Now, if it's hot enough and you can squeeze enough together, you might squeeze more protons. Now, what I've done here is taken one proton called hydrogen. It might have an electron or it might not, but we still call it the atom of hydrogen. When you squeeze it together, we've got helium, but something else happens a little more complicated. That's the essence of stars. We'll come back to that. Making stars shine, the nuclear fusion, making stars shine. This makes stars shine or glow as they build bigger and bigger atoms. And we will talk about that sequence. They build them, they fuse bigger and bigger atoms. A lot of people say burning, and it's not burning. So that's just an analogy. Okay, so that's what's up with stars. Well, let's talk about the range of stars. So I made up this analogy. I thought, let me give you an idea, and then I'm going to show you some pictures. There's quite a range of stars out there. So don't overthink this. All right, I just made this up. There's a range of stars. It's not literal, but it's really good. I mean, it's really good as a star. This is an introduction, right? So I thought of adult males. I thought, okay, adult males might fall. Maybe you can put women in there. I'm not sure if there have been any 8-foot women. I just don't know. So I'm just going to go with this, right? And let's think about basketball. And if you watch the women's NBA, of course, you know that they're incredibly talented. But let's go with the men's NBA basketball. And we can think about playing basketball, which I grew up doing and do love doing. So we look at these and you go, okay, certainly people can be shorter than 5 feet. Don't worry about it. Anyway, this does a lot for categorizing stars. Like how much mass, remember? We need the mass. Right? We need the gas to have the mass, to have the gravity, to have the fusion. So this kind of is related to a variety of things. And so another question that comes up is, how big is our sun? Is it a big star or a small star? A lot of people say it's an average star. I mean, in some characteristics, I don't know if average, I don't think average is quite the right word we want. Let's explore this. So this dot with a circle, remember that symbol? A dot with a circle as a subscript. So the mass and the subscript, a dot with a circle. It's kind of like heliocentric with sun at the middle and planets going around. However you want to think about that, that would be the mass of our sun as a reference. You know how we compared everything to Earth when we were looking at planets and moons? Well, now we're going to compare things to sun so that we see where sun fits in. Now, people are still looking for some of these things. So this is not absolute, but our sun is kind of like a 6 foot tall person, right? So 6 foot, if you think about it, males, you know, where are most people? This is important. Where are most adult males on this spectrum? Well, most of them are here, right? It's important. Fewer adult males are over 6 foot, right? They're there, but they're fewer. And even fewer are in there. You know, not really that many, right? I'm going to talk about this. So what am I talking about? Well, when it comes to stars, so that's adult males, and that's the analogy. Stars, sun is about here. Right? It's pretty tall, if you will. 6 foot is, you wouldn't say to a 6 foot person, you're short. You know, you would say, you're too tall to be a gymnast. There are times when being tall is not so good. You might say, you're going to have a hard time making the NBA. Some people have done it, but 6 foot's pretty short. That's why there are these great, which I like, 6 foot and under leagues for basketball. It's like, I'm tired of getting my jump shot from the top of the key blocked by someone that's in the key. Like, that's so frustrating. So there are these leagues. And if you're in a 6 foot and under league, you are tall. With a star, you are big. And you wouldn't say you're average, because there are some that are quite a bit bigger, but most are smaller. Most are smaller, so the average actually is in here, right? How small can a star be? How little mass? Well, about, so just, you know, easy numbers, about 1/10 the mass of our sun. So if you take our sun, the gas, divide it into 10 groups, and one of those groups, 1/10, and I'll tell you about the size in a second, the mass of our sun. Or maybe smaller, you know, we'll talk a little. Up to, now this is still being sought after. You could say 100, it'd be easy, 110, 100. That's good. 100 suns worth of gas. Take 100 suns and put them together, all that gas. 150, maybe 200. Check it out. Do a search. See the largest star found, and see if it's verified or, you know, they're checking it out. But you get the idea that our sun is not exactly halfway in between. By any means, there's a lot of really big ones. But when I say a lot, there's a lot more smaller ones. So overall, you know, it's like a 6 foot tall person, right? You know, not short, a little tall, right? Walking in a crowd, who would you see? Even though most people in the crowd, go around the world, you'll see. Most people in the crowd are going to be in here, right? Most people in the crowd are here. try finding my grandma. She's over here, right? Actually, she's down here. She died. Anyway, try finding her, right? Or try finding your kid in the crowd. Even though there aren't very many of these, you can sure find them. You watch an NBA team walk around, you can find them. There they are. There's not very many of them, but you sure find them, right? Easy to find. I got a friend who I ski with, 6'5". He's easy to find. There you are. I got you. So think about what I just said. What does that mean? We're connecting this with stars. Which stars are you going to tend to see? Even though most of them are down here, you're going to tend to see big ones, right? So we'll talk about that. We see ones that are giving off a lot of light and close within our galaxy. Okay, so who do you see? In fact, discovering more small ones with better telescopes because they're harder to see. So that's an interesting point. And this analogy does really well with that. The other analogy is this. Let's take a look here. How many Jupiters would make our sun? Well, to make our sun, it would take about the gas. Remember, Jupiter has a kind of a solid core at the center. Stars do not. Jupiter's a want-to-be star. It could have been, but let's see how far off it was. Jupiter, to make our sun, it would take 1,000 Jupiters worth of gas. 1,000 Jupiters. So it's like, to make our sun has about 1,000 times more gas than Jupiter. Remember, you can get about 10 Jupiters across our sun, the width of our sun, diameter of our sun. And then 10 this way. 10 times 10 is 100. And then 10's this way. 10 times 10 times 10 is 1,000. About 1,000 Jupiters worth of gas. Okay? How wide is it? Our sun. Well, you know that. I just told you, right? 10. 10 Jupiters wide. And Jupiter's about 10 Earths wide, or 11. Right? So remember that. Okay, 10 Jupiters wide is our sun. What is it? What is small? What's like the smallest star? Here's the question. Think about this. What is enough mass? Jupiter didn't have enough mass to have enough gravity to have this nuclear fusion going on in the center. So it's got a solid core. It's just not got enough gas to have enough mass to have enough gravity, right? Jupiter doesn't. But how much would be enough? You know, if you double Jupiter, do you get, well, it's something on the order of, I don't know, just to give you a sense, I kind of want to say 64, but I'm going to say, like 75. So this is not an absolute number, and you could look up what's the smallest star found. But there's a limit. Any smaller, and you've not got enough mass, you've not got enough gas to have enough mass, to have enough gravity to create the fusion. That's stars. And so that's all it is. You need enough gas to have enough mass, to have enough gravity to cause that fusion, the squeeze. How wide would that be? About 4 Jupiters wide. 4 Jupiters wide. So we've got sun, and you could draw that, right? Draw a circle for sun, and then draw 4 of them. Wait a minute, that's sun. That's why you got to do this stuff. I know this stuff can get tangled. Remember what you're talking about. You draw a circle for Jupiter. Draw a big circle for Jupiter, you can get 10 Earths across, or 11. Now make Jupiter small. Here's 1 Jupiter. That's a Jupiter. Then I go, that's the smallest star. Keep going, go 10 across, that would be our sun. So you really start to see, right? That would be our sun. You do that. the sun is pretty big compared to this. 6 foot, it's only 1 foot taller than 5 foot. But if you're down here, you get to be a gymnast, right? You could be a gymnast if you want. There's certain things that you want smaller for, whatever. You get what you get, you know? So, that's about the range. And you can look this stuff up, but I thought it was interesting to see how much gas do you need? Well, you need about, 75 Jupiters. So Jupiter was pretty far off when it comes to being a star, when it comes to having enough gas, to have enough mass, to have enough gravity, to create fusion, to make it glow. We're going to talk about those cycles. So sun, I would say, is mid-range, but it's big. I mean, it's big. I know these are huge, huge. Let me show you in just a moment. Those are huge, huge. But most of them are here. So walking in a crowd, that's going to be reasonably tall. Reasonably tall in a crowd. Because there won't be many. These will be easier to see. Okay, you got that? So average, I'm not sure that the term works that well. It's okay though, you can think about it. So it's big compared to most stars. But there are some incredibly tall. So if you're 6 foot and you walk around, you go to NBA court, and you see a person that's 6 foot in the NBA, occasionally there are, and you see them and they're like, but it's amazing, it's just a foot, you know? Come on, it's just a foot. 6'6", Michael Jordan, or whomever else that you want to, 6'3", Steph Curry. Let's talk about this. And what I'm going to do here is come back over, and I'd like to review a little bit on sizes. So we talk about how big. Okay, so let's come back over here, and I'm going to talk about how big. And let's review this just real quickly. Think about all that you've learned. And so you say, is Earth big? Yeah, it's the biggest inner planet, right? It's big enough to stay warm, right? So there it is. And that's good. And then you go, okay, well, is Pluto big? No, Moon is actually bigger than Pluto, so. Oops, let me get this. Oh, well, is Earth big? Well, it depends on what you're talking about. The terrestrial planets, yes. 4 Earths across Uranus and Neptune, 10 or 11 really, across here, 9.5, but we can say 10 and 10 across here. But Jupiter, we know you need like about 75 Jupiters worth of gas to make a star. And once you have that, you have enough gas to have enough mass, to have enough gravity to create nuclear fusion. That's all you need. That's the only requirement to be a star. And so then we know though, and we say, is Sun a big star? Well, we do know, right? So I can count this across, 1, 10. We do know that there are smaller stars. In fact, we do know, like 6 foot, most stars are smaller than Sun. There's kind of a reason for that too. So there are interesting questions that come up. Remember, these are broad strokes. So interesting questions come up that are still being researched. Don't take this entirely as absolute, but this is good. So 1, 2, 3, 4, a star like this would be like the smallest star. 4, 1, 2, 3, 4 Jupiters across. Okay, so that would be like the smallest. And so from that down would be where most stars are. But what about those big ones? I mean, they sure are fun to look at, right? And let's see how big they can get. You might have heard some of these names. Look at Sun. Oh no. There's our Sun. Sirius, the brightest star in our sky besides Sun. It's big, it's close, it's hot. It's giving off a lot of light. Think of it as a white star, we talked about it at the beginning, right? Pollux, one of the Gemini twins. Whoa, that's big. I don't know, maybe that's a 7-footer. Maybe that's a 7-footer. What's that? Is that an 8-footer maybe? Let's follow Arcturus. Ready? Let's do this. There goes Arcturus. Watch Arcturus. Oh, sorry. 7 foot, maybe in the 7-foot range. But where's Sun? It's 1 pixel. Sirius, Pollux, Arcturus, Rigel, Aldebaran, Rigel in Orion, foot of Orion, Aldebaran in Taurus, Betelgeuse, the shoulder of Orion, Antares, the heart of the Scorpion, Scorpius. But those are, again, just great patterns, and you can make up your own stories and patterns. So they get pretty big, I would say. They get pretty darn big compared. All right, let's go back. So that's my analogy, and I think it works pretty darn well. But let's talk about this a little bit. And some details that are quite important. We're going to get into this in the next few videos. Right. If you have more mass, you're going to have more gravity, which means it's going to go. So you're really going to squeeze those protons together. What strongly? It's like. Well, I'll talk about a bag of glass, but you're really going to make those snap together. And so you're going to have shorter lives. Whereas if you have less mass, you're going to have less gravity and slower fusion, kind of a smoldering fire. But it's not burning. It's not burning. It's fusing. Slower fusing and longer lives. Hey, here's a question. I'll let you research it. I'm not going to give you an answer. And is there an answer? Do we know? We still research it. Could it be that we have fewer big stars? One reason we'd have fewer big stars is that they just don't form as much. Another reason would be what? In that star formation, I mean, did stars form more before, and are they going to form as much now? And in the star formation, do just fewer of these form, or do they just live shorter lives so you don't see as many because they go? Interesting questions. I'm not going to give you an answer. So shorter lives, longer lives. Sun, kind of mid-range, but there's a huge range, so it's not in the middle. So look it up, but just to give a sense, Sun's total life, 10 billion years. We know that we started 4.6 billion years ago, so about 5 billion years. So we're about halfway through our star's life. It can't last any longer. How's it going to die? What's it going to do? We're going to talk about that. You need enough gas. It's not a choice. It's not an opinion. It's not a desire. It's just, you just need enough gas to create that fusion. And your life will depend on how much gas that ball starts out with. We call these low mass, high mass, and very high mass. Very high mass. And you can categorize them more than that, but that's a good starter. And Sun would be in the low mass. Sun is in the 6-foot and under basketball league. So it's a big one, but it's a low mass. And you kind of saw that over there, right? Now we're going to categorize these and we're going to chart this on the HR diagram. We'll talk about that. So let's begin to increase your familiarity with that. Something called spectral class and color is related to this. And you really will get quite an understanding of stars. When you step under that night sky, you're going to be able to really think about that. And the degree that you can hold on to details will be the degree of richness that you'll be able to enjoy. Okay, so there's something called spectral class. Now, it turns out
think we're gonna pull in Wien's law. Remember Wien's law? You pick out the brightest frequency, or the frequency given off the most, not the highest frequency, however I did that, not the lowest frequency, not the average frequency, but the one frequency of light that the star gives off the most, or object. Remember Wien's law? So it was related to temperature, wasn't it? As an object got hotter, then it gave off higher and higher frequencies. And the one frequency given off the most became higher and higher. And we combine all that light that we see